Imagine a massive, tightly packed atomic nucleus. When a single, slow-moving projectile strikes that heavy target, the nucleus destabilizes and breaks into two lighter pieces, ejecting new projectiles and a flash of liberated energy. This process is provoked nuclear fission. It requires an external agent, the neutron, to intervene and stimulate the division of the heavy nucleus. The mechanics are represented by this baseline equation. On the left, a neutron collides with the target uranium-235. On the right, the reaction produces two lighter nuclei, additional free neutrons, and the resulting energy. For the uranium to successfully absorb this neutron, the particle must be moving slowly. These are thermal neutrons, carrying a specific kinetic energy of approximately 0.02 electron volts. Breaking the atom releases energy, but to harness this power safely, we have to account for every single subatomic piece before and after the split. Consider a reaction where uranium-235 splits into krypton-90 and barium-142. In this specific equation, the number of emitted neutrons, represented by the variable y, is currently unknown. We find y by applying the law of conservation of mass number. This law requires the sum of the top mass numbers on the reactant side to be perfectly equal to the sum of the mass numbers on the product side. We can extract these values into a simple algebraic formula. On the left, we add 235 and 1. On the right, we have 90 plus 142. Note that the unknown coefficient y must multiply the mass of the neutron. Instead of just adding y, you must calculate this term as y times 1. With the algebra simplified to 236 equals 232 plus y, pause the video here and solve for the value of y. The math resolves to a value of 4. This specific fission reaction emits exactly 4 new neutrons. This reaction generates more neutrons than it consumes. That mathematical surplus is the physical mechanism that turns a single reaction into a self-sustaining cascade. As shown in this diagram, neutrons emitted from the initial split move outward to strike neighboring uranium nuclei, triggering the next generation. It is the physical collision of these neutrons that provoke subsequent fissions. This creates an exponential geometry. One neutron triggers a split that releases multiple neutrons, which then trigger multiple new reactions, scaling the energy output in a fraction of a second. In a civilian power plant, this chain reaction is strictly controlled. Engineers use materials to absorb excess neutrons, ensuring the fission process remains safe. If those thermal neutrons are not managed, the chain reaction runs out of control. The result is structural destruction and the release of radioactive materials. Fission offers massive power, but requires constant, precarious control of an unstable chain. This led nuclear physicists to explore a different path, the process that powers the stars. Nuclear fusion is the opposite of fission. Instead of splitting a heavy atom, fusion binds two light nuclei, such as deuterium and tritium, into one heavier nucleus, which liberates a neutron and a massive pulse of energy. The obstacle to this process is Coulomb's law. Because the nuclei are both positively charged, they repel each other with immense force, preventing them from connecting under normal conditions. To overcome this repulsion, the particles must be given extreme kinetic energy. This requires heating the fuel to approximately 10 to the power of 8 Kelvin, allowing the nuclei to smash through the barrier and fuse. For equal masses of fuel, fusion yields more energy than fission. It utilizes hydrogen, an abundant, inexpensive fuel source, and avoids the creation of heavy radioactive waste. This summary table compares the two processes for your exams. Note the differences in their triggers, the mechanics of the reactions, and the nature of their byproducts. Whether we are splitting heavy elements or merging light ones, the key to unlocking nuclear energy lies in mastering the laws of mass conservation and the forces governing the subatomic world.